Hi, hope you are well. In this video, we want to solve these hard Stanford 2022 problems. And please don't forget to subscribe to have next videos and thanks for your support. So let's solve this problem. For this problem, we need some important things and useful things. At first, you should know congruency is what. You need this for many high school exams, competitions. If you want to apply for top university, you should know this sign is what. If, for example, any student don't know congruency is what, feel free to send message to my WhatsApp number in the description or comments. Also, maybe I will release some tutorial things for congruencies for the students don't know, because if you know this tool and divisibility, here we don't need divisibility, then you can solve around 80% of the problems from round 1 qualifying level, basic level, up to international level. But for this problem, we want to solve this problem at first with little Fermat's theorem. Little Fermat's theorem is what? So let me tell you. Suppose P is prime, so we call this one lemma 1. Okay? We want to use lemma 1 and lemma 2. It's a name, for example, the like theorem. So if P is prime, then A to the power of P is congruent. Let me tell for the students or for the subscribers that don't know, this means what? It means that the remainder of A to the power of P and remainder of A, when divided, we write mod P. When divided by P, they are equal, the remainder. For example, let's check for example, if P is 7, and if we check 2, 2 to the power of 7 is congruent to 2 mod 7. It means both of them have same remainder. 2 to the power of 7 is what? 1 to 8. And if you divide it by 7, it will be what? 7 times 1, 58. And okay, so 8 times 7, 56 plus 2. So as you can see, the remainder, both of them are 2. It was lemma 1. Lemma 2, that is useful in also summer camps of America, Olympiad exams, also in many admission exams of top universities. If you want to apply for them, lemma 2 is what? Lemma 2 is order. It means what? Suppose that A and P are relatively prime, or let me write P is prime again, or let me tell you, let's solve this for general number. Okay, so now here, suppose n is an integer and a and n are relatively prime, means GCD of a and n is 1. Suppose d is a positive number, that a to the power of d is 1. Mod what? Mod n. So, and suppose d is minimum number, positive integer that satisfies this, then we can say what? We call this the order of, we call this one order of a mod n is d. We call this one. It is definition until here, order. So if someone says order, it is this. And now we want to say what? If, for example, suppose m is a positive integer and a to the power of something is also 1. Then we want to say what? We want to say d divides m. I will prove lemma 2. Lemma 1 is so much famous, little Fermat's theorem. You can find it on net. If you search, if you wanted also the proof of lemma 1, because it's famous theorem, feel free to send message to my WhatsApp number in the description and comments. Now, let's solve this one. Proof of lemma 2 is what? You say, okay, suppose m is dq plus r, and r is remainder. R is greater than or equal 0, less than what? D. We know a to the power of m is what? A to the power of dq plus r. And you can say it's a to the power of d to the power of q times a to the power of r. and we know it is what? A to the power of D, because it is order, we know it is 1 by the definition. So it will be 1 times A to the power of R, and we know A to the power of M is what? Is 1 mod what number? Mod N. So we found what? R. If R is positive, R is less than D. And by the definition, D was the minimum, that A to the power of D is 1. Now R is less than D, so R should be only 0, because if R is positive, then we found a number that is less than D and positive that satisfies A to the power of that is congruent to 1. But by the definition of order, D was the minimum. So here we proved one of the most powerful and important things in number theory, that if you have order, so look, let me tell you, I tell terminologies of this order, little Fermat's theorem. If you want, you can search on net. There are a lot of problems, a lot of things about order and Fermat's theorem now, and congruency. So we want to use lemma 1, congruency, we said, and little Fermat's theorem, and order. And order of, for example, A mod N. We want to use these three definitions and the lemma that we set to prove this Stanford problem. Okay, let's see the problem again. Okay, so here we say, suppose that P, it is multiple of P. P is a prime number. So 220 to the power of 22 plus 1 mod P is 0, because it is multiple of P. I told you that the remainder is 0. So it is like equality for subtraction, addition, and division. So if we subtract 1 from both sides, then 20 to the power of 22 is negative 1 mod P. Now, if we raise both sides to the power of 2, it is like equality, congruency. Raising to the power of 2, it's multiply this by itself. It is congruent to 1 mod P. Now, we've reached this also by little Fermat's theorem. We know that 20 and P are relatively prime numbers, because if P divides 20, then P divides 20 to the power of 22, and P divides, and we know P divides this number, so if it is multiple of P, so P divides this one by here, so P divides 1, and that's contradiction. So here we can use little Fermat's theorem, and 20 to the power of P minus 1 is congruent to 1 mod P. It is little Fermat's theorem. Now we want to use order. Suppose order of 20 mod P is D, and it's the minimum, so 20 to the power of D is congruent to 1 mod P. And now let's see, we can conclude what? Because 20 to the power of 44 is congruent to 1 mod P, we said D is minimum by lemma 2. We said the order divides D divides 44. Where we said that? Here. D divides M, any number. So the order D divides 44. So D is the divisor of 44. And now we know 20 to the power of 22 is not negative 1. So if D divides 22, this part, so we know that 20 to the power of 22 will be 20 to the power of D, for example, cube. And then it is congruent to 1 mod P. And that's contradiction. Why? Because then we know 20 to the power of 22 is negative 1. Then if we take negative 1 to right hand side like equality, this, so P divides 2, so P is 2 divisor, but this is even plus 1, an odd number, and that's a contradiction. So we conclude, because we've reached contradiction, D doesn't divide 22. So what are the case for D? D divides 44, D doesn't divide 22. So the only case, if you write all divisors of 44, it is 1, 2, 4, if you want to calculate the number, it is 2 squared times 11, 3 times 2, 6, 6. Divisors 1, 2, 4, and the next one, 11, 22, 44. So the only possible cases for D is what numbers? 4 and 44 that are not divisor of 22. So D can only be 4 and 44. Now we consider D equal to 4 and D equal to 44. These two things. D equal to 4 means what? 20 to the power of 4 is congruent to 1 mod P. And then we can say what? We can say 20 to the power of 4 minus 1 is congruent to 0 or multiple of P. So we can write it is 20 squared minus 1, 20 squared plus 1. And again, write 20 squared minus 1 as 20 minus 1 times 20 plus 1 times 20 squared plus. So if you check these numbers, the first one is 19, the second one is 21, which is 3 times 7, and the last one is 401. It is for the case that D is 1. Now, if we check these numbers, we want to see 20 to the power of 22. The condition is mod P should be equal to negative 1. So if we check 3, 7, and 19 for all of them, 20 for 3 and 7, 20 is congruent to negative 1 mod 3 and 7 also for both of them. I don't want to write two congruencies. It is congruent to negative 1. It means mod 3 and 20 is congruent to negative 1 mod 7. So here we can say what? Or let me tell you a better thing. Do you agree 20 squared minus 1 is this? So we can say 20 squared because negative 1 is this. So 20 squared is congruent to positive 1. So if you consider 20, raise both sides to the power of 11. So 20 to the power of 20 is 1 mod, let me write also 19. It's congruent to 1 mod 3, 7, and 19. But we know 20 to the power of 22 is negative 1. And that's a contradiction. So 3, 19, and 7 don't work. Now if we take 401, 20 to the power of 22 mod 401. So if you consider mod 401, you can say 20 to the power of 20 is 420 squared to the power of 11. Because I can write it is 20 squared to the power of 11. And 20 squared is 400. 400 is congruent to what? Mod 401, negative 1. Negative 1 to the power of 11, which is congruent to negative 1 mod 401. And it works. So we understand one prime factor of 2 to the power of 2022 plus 1 is 401. But the problem says what? Find two minimum prime factors. So if we find two minimum less than this, then we don't calculate this. If we can't, we calculate 401. So we've considered, let me write case 1, that D equal to 4. We finished this part, only 401 works. P. Now let's consider case 2, which D equal 44. So if you pay attention here, D is 44, and we said D is what? D is order. And by little Fermat's theorem, 20 to the power of P minus 1 is congruent to 1 mod P. And we know because D is order, D, if we combine lemma 1 and lemma 2, D, we said divides anything that is any power, the 20 to the power of that is congruent to 1. So D divides P minus 1. we use this, and here we say, okay, in this case 44 divides p minus 1. So p is what? It means p minus 1 is multiple of 44, this sign. As I said, divides, we say this. Okay, so p minus 1 is 44, for example, q. And we can say p equal to 44q plus 1. And then we should check, for example, if q is 0, I check for some of them 44, the next one 89, this one plus 44 is 3, and 13, 133 plus 44, 177 plus 44, 11, we have 1 plus 7, 8 plus 4, 2, and 2, 1. The next one is 2, 6, 5. The next one is 9, 0, and 3. The next one is 3, 5, 3. And the next one, 44, is 3, 9, 7. I want to check until these numbers, so we should check which of them are prime. So the next one, 45, the first one, is multiple of 3 contradiction. This one is multiple of 7. This one is what? 3 times 15. This one is what? Is 7 times 1, 63. It's 9. It's bad. It's not prime. This one is multiple of 3. 3 times something. It's bad. 2, 1 is multiple of, let's check. Okay, if you divide by 13, it will be 13 times 1, 13. Then 91, it will be 7. And it is bad, it's not prime, it's multiple of 5 times something, it's bad. It is multiple of 3, it's bad, you don't need to check. So we need to check 89, 353, 397. And after checking all these cases, we know 401 works. We want to find 2 minimum prime factors of 2 to the power of 20 to the power of 22 plus 1. So let's check. Our number is 20 to the power of 22 plus 1. We want to see which of these numbers works. So let's consider 89 at first. We only need to check these 3 numbers. So 20 to the power of 22 plus 1, or let's consider this one, mod 89. We want to calculate this. Okay, we can say it is what? 2 squared times 5 to the power of 22. And let me write mod 89 at the end to be able to write many things. And it is what? 2 to the power of 44 times 5 to the power of 22. Now, if you check 2 to the power of 6 mod 89, it is 64. And mod 89, you can subtract 89 from that. It will be negative, if we check 5, negative 25. So here it is congruent. 2 to the power of 6, you can say it is 2 to the power of 6 times 7 times 2 squared times 5 to the power of 22. And then we can say 64, negative 25, power of 7 times 2 squared, or you can say, you can write, for example, 2 squared of 4. Let me write like this, 5 to the power of 22. And it's congruent negative. It is 5 squared to the power of 7. So you can write 5 to the power of 14 times 2 squared times 5 to the power of 22. And it's congruent to negative 5 to the power of 36 times 2 squared. Now, if you check 5 to the power of 4, let's check here. 5 to the power of 4 is 625. And if you check mod 89, it will be 7 times 89. It's what? 63, 6, 7 times 8, 56 plus 6, 623 plus 2. So it is congruent, it is multiple of 89, so it's congruent to 2. So here we can say, okay, it is equal to negative 5 to the power of 4, the power of 9 times 2 squared. And 5 to the power of 4 is congruent to 2. So negative 2 to the power of 9 times 2 squared, which will be negative 2 to the power of 11, and it is equal to negative 2048. And if we divide 2048 by 89, so we can say 2 times 9, 18. We have 1. 2 times 8, 16 plus 1, 17. 14 minus 8, 6. It is 10, 9 minus 7. You can say it's 2. 2, 6, 8. And if you multiply by 3, 3 times 9, 27. 2, 3 times 8, 24 plus 2, 26. It's 1. So because it is 1, so it is negative 1 mod 89, and the thing that we wanted. So P for 89, if P is equal to 89, then we can say 20 to the power of 22 is negative 1 mod 89. So 20 to the power of 22 plus 1 is multiple of 89. So we know 81, 89 is the answer, but the problem says find if the multiples of P1, P2, P3, P4, it says find P1 and P2. So in our case, P1 is 89, the smallest one. Now we don't know. 353 is the answer, 397 or 401. If we want to prove these two numbers are not divisors, so we can say the next one is 401, and then the problem will be solved. So let me copy these two numbers. Okay, at first I reject 397. I say, okay, 20 to the power of 22 is congruent mod what 397. So you say it's 20 squared to the power of 11. It's 400 to the power of 11 and is congruent to 3 to the power of 11. And okay, here we can say it is equal to 3 to the power of 6 times 3 to the power of 5, which is 729 times 243. And if you subtract 2 times this, 729, it will be negative 65. Look, 729 is equal to negative 65. If you subtract twice of this number, it will be this times, oh no, this part, let me correct it. You can say if you subtract twice of this, 23 is left if you calculate. So it is congruent to 23 mod 397. And sorry, the previous one was correct. I just told you for 353 this case. Okay, so negative 65, it's okay, times 243. If you subtract 397 from 243, it will be 154. Now here you can say it is what, negative 13 times 5 times this number. 5 times this number is 25525 plus 227, 770. And this one is congruent to negative 24. And now if you multiply this new number plus 13 times 24, because negative and negative will be cancelled, it will be 312. And it's obvious the remainder is 312, not negative 1, because negative 1 is congruent to 396 here. So that's contradiction. We've rejected 397. Now the last step of the problem, we want to also reject 353. So let's consider 20 to the power of 22, this time mod 353. Okay, this time we split up 20. We say it is 20 squared times 5 to the power of 2020, which is 2 to the power of 44 times 5 to the power of 2020. Okay, so we want to see, is it congruent to negative 1 or not? So if we consider 2 to the power of 44, we can say what? We can say it is congruent to 2 to the power of 10 to the power of 4 times 2 to the power of 4. 2 to the power of 10 is 1024 to the power of 4 times 24. And if we want to see 1024 is congruent to what mod 353, if you subtract 3 times 353, then we will see negative 35 to the power of 4 times 24. And we can say, let me write again here, mod 353. Okay, so we can say what? Negative will be cancelled because it is to the power of 4. And sorry, here I should write 2 to the power of 4, not 24. Now we can say it is equal to 2 times 35, 70 to the power of 4. And we can say, okay, 70 squared to the power of 2. And it is 4900 squared. Okay, and we can say it is congruent if you subtract 14 times 353. If you divide it, then it will be negative 42 squared, or you can say 42 squared. And if we calculate 42 squared, it will be 1764. And if you subtract by 5 times 353, it will be negative 1. All of them were mod 353, 353. So here, because it is negative 1, we conclude, okay, so this part we've calculated is negative 1. So we conclude 5 to the power of 2020 should be plus 1. So that plus 1 times negative 1 will be negative 1 mod 353, that is prime number. So we understand that 520, we want to prove it that it is impossible by contradiction. So it is multiple of 353. So let's calculate this. It will be 5 to the power of 11 minus 1 times 5 to the power of 11 plus 1. Because when 353 is a prime number, when this number is multiple of p, that p is prime here, so p divides this or p divides this. So we conclude 5 to the power of 11. If this one is multiple of 353 plus 1, it's congruent to plus 1. If this one, negative 1. Mod, or, let me write or, this one, mod 353. So now our goal is to find the remainder of 5 to the power of 11 mod 3 to the power 353. It's the last part of the solution. Okay, we can write it is 5 to the power of 4 times 5 to the power of 4 times 5 cubed. 5 to the power of 4 is 6 to 5. 6 to 5 squared times 5 cubed, 1 to 5. If you consider 6 to 5, 6 to 5 is congruent to negative 81, so it will be negative 81 squared times 1 to 5, and is congruent to 3 to the power of 8 times 1 to 5, and it is equal to 3 to the power of 7 times 3 times this, which is 3, 7, 5. And we can say it is congruent to what? 3 times 3 to the power of 6 is 729. 375, if you subtract 353 from that, it will be 22, so it will be 66. 3 times 22 times 729. Okay, and instead of 729, we can say if you subtract twice 353, it will be 23. And if you multiply these two numbers, it will be 1518, which is congruent to 106. Now, 106 is not 1 and is not negative 1. So 353 doesn't work. So our prime numbers, one of them we proved was 89. The other one was 401. And the problem says, what's the sum of them? 9 plus 1, 10. We have 1, 1 plus 8, 9, 490. Okay, so we've solved this hard problem. A lot of idea we've used. It improves your problem solving in number theory. I will release other problems and each video, because some subscriber wants I will describe from basic level, and gradually we will consider all parts of the problem. But again, if you had any problem about the solution of this problem or other problems, feel free to send message to my WhatsApp number in the description and comments. And please don't forget to subscribe. Thanks for watching the video and for your support. Bye.